All right, so we just got done talking about all the different characteristics of rational functions. We've talked about holes, vertical asymptotes, and horizontal asymptotes. So now let's actually take a function, pick out all of those characteristics, and use them to graph what this function might look like. So I want you to put your graphing calculators away. I want to be able to do this without relying on a calculator. You should be able to sketch a pretty decent graph just by knowing those different characteristics, okay? So let's look at example number 4a. We have this rational function. Let's first start off by factoring it so we can see all the little factors or pieces so that we can pick out those characteristics, holes and asymptotes. So pause the video. I want you to factor the numerator and the denominator of this rational function. All right, well, it looks like the numerator is already factored. X plus 1 can't really be broken down any farther. The denominator, though, can be factored, and hopefully you found factors of 2x minus 1 and x plus 3. Now, it doesn't look like there's any factor on the numerator that can reduce with any factor of the denominator, so it looks like this is in most simplified form, which means there are no holes in this graph, right? But there are some things, some x values that are going to cause this denominator to equal 0, right? Which are going to cause us vertical asymptotes. There's two of them. Where are they? Well, it looks like there's vertical asymptotes at x equals -3 and x equals positive 1/2. So we can draw those vertical asymptotes on our graph, again at oh, did I say y equals those? I'm sorry, should be x equals, right? Vertical asymptotes at x equals -3 and x equals 1/2. So kind of in between 0 and 1. Those are my vertical asymptotes. Remember, no holes. All right, let's look at horizontal asymptotes. As I'm looking at the degree of the top, it looks like the degree is 1. It looks like the degree of the bottom is 2. So if I'm comparing my P's and Q's, it looks like P is less than Q. And do you remember when P is less than Q, if the degree of the top is less than the degree of your bottom, what does that mean about a horizontal asymptote? Do you have one? And where? So hopefully you said that we have a horizontal asymptote at y equals 0. So if I'm graphing this horizontal asymptote, I know that there's going to be a horizontal asymptote at 0. So as x approaches -infinity or as x approaches positive infinity, our graph is going to, quote, get stuck at that y equals 0 horizontal asymptote. All right. Maybe talking about x and y intercepts will also be helpful. Another key characteristic that helps us kind of graph our function a little bit more accurately. So let's first talk about x-intercepts. We can find x-intercepts when the y value is 0. So taking our function, plugging in 0 for y or for f of x, and solving to see where it touches the x-axis. I can take this and I could cross multiply, or I can really imagine I have a fraction. The answer has to equal 0, so what piece of my fraction, the numerator or the denominator, must be 0? Well, the top, right? Because our denominator can't be 0. We're not allowed to divide by 0. And so if I set that top equal to 0, I've just found an x-intercept at x equals -1. So I know also on my graph that my graph is going to touch the x-axis at -1, -1 comma 0. What about y-intercepts? We can find y-intercepts by plugging in 0 for x. So in my function, let's plug in 0 for all of the x values in the numerator and the denominator. Let's simplify, and it looks like there is a y-intercept at -1/3. So when x is 0, it's going to cross the y-axis just barely underneath 0 here, yeah? So that kind of gives us a guide, especially in that middle piece, that we know we have to go through -1/3 on the y, but not touch the vertical asymptote. We know we have to go through -1 on the x, but not touch this other vertical asymptote. So I can kind of imagine that my graph's going to look something like this in the center, right? Now, what is it going to look like on the outskirts? What is it going to look like to the right of that vertical asymptote at 1/2, or maybe to the left of the vertical asymptote at -3? And without using our calculator, we might have to kind of, like we did back in the day, make a table of values, or at least see what's happening with my y values when x is 1, or when x is 2, or when x is 3, over here on the right side of my graph. So I'm just going to pick one of the values. I'm going to pick x equals 2. And I'm going to plug in 2 into my function so I can figure out, does my graph end up being positive, the y values being positive, or are my y values negative? And so then I have a better idea of where to graph the rest of my function on that right side, okay? So if I plug in 2 into my original function, on the numerator I have 2 plus 1, that's 3. If I plug in a 2 to the denominator here, that's 2 squared, which is 4, times 2, which is 8. 2 times 5 is 10. Whoop, 2 times 5 is 10 minus 3. So I have a 3 on my numerator, and 8 plus 10 minus 3 on my denominator. I ended up getting a y value of positive 1/5. So when x is 2, y is positive 1/5. So I know it's up here. And so that gives me a good idea that I know I have to hit through that point. I need to get close to this vertical asymptote at 1/2 but not touch, and I'm going to get close to the horizontal asymptote at 0 but also not touch it, right? Do the same thing over on the left side of -3. I know that there is a vertical asymptote at -3, but is my graph up above or down below this horizontal asymptote, right? So pick a number on the left of -3. Pick an x value like -4, -5, -6. Plug it into your function and see what your y values come up as. Do they come up as positive? You need to graph it on the top. Or are they negative and you need to graph it below? So I'm going to pick, I don't know, x equals -4. Plug in -4 into your function. If I plug in -4 to the top, I get a -4 plus 1, which is -3. If I plug in a -4 to the denominator, -4 squared is 16. 16 times 2 is 32. -4 times 5 is -20. And then I have my -3. So simplifying it, I ended up getting a -3/9, so -1/3. And so I know that my graph then, when x equals -4, I need to be down here in the negative values. So then I know exactly, well, maybe not exactly, but pretty darn close, where my graph needs to be graphed in order to go through that point, but not touch my asymptotes, okay? So this is a pretty darn good sketch of what my graph looks like without a calculator, just knowing all those key characteristics. Now, if you're a visual person and you want to double check, take out your calculator, graph this function in your calculator, and it should look really, really close to what we just graphed by hand without a calculator.